Hey, welcome back. In this lecture, we are going to be looking at different implementations of the, two different implementations of an algorithm, let me rephrase, two different algorithms for detecting a minimum spanning tree in a graph, and then in the next lecture, we'll look at how we would actually implement those. We're going to look at the algorithms today, and the two of them are definitely distinct, so it's not two different implementations of the same algorithm. I misspoke earlier. We're going to start out with this graph. And typically when we deal with minimum spanning trees, the graph will be undirected. You can deal with things with directed graphs as well, but we're not going to be covering that here. And so here we have A, C, G, D, E, H, F, and B. And here we have 13, 3, 15, 1, 2, 9, 1, 6, and 6, and 8, and 5, and 7, and 11, and 4. This graph will get a little bigger when we really start writing directly on the graph. And this should be probably showing up right next to you as a slide. But that's the graph we'll be dealing with. Now, the idea of a minimum spanning tree requires that we first understand what a spanning tree is. And an example of a spanning tree is what I'm drawing here. The idea of a spanning tree is it's a tree that spans the entire graph. And so I could have perhaps here D and E, and maybe I have E connected to B, and E connected to G, and G connected to C, and C connected to A, and then we also have here E to H, and H to F. So we can go ahead and write these edges in, the weights of the edges we're actually using here. Notice what we've done is, since we want to connect the entire graph, what we're trying to do is connect all the vertices. So a spanning tree will have every vertex of the graph inside the tree itself, and it will also have v-1 edges, because a property of a tree, which you probably saw in a discrete math class, is that if you have v vertices or v nodes and the structure's connected, and it's a tree, then you have v-1 edges. The idea would be if you add an edge anywhere else between any two vertices, you'll create a cycle, a path that can go back to itself, and we said that we don't have that for trees. Now, this, of course, isn't the kind of tree structure we've looked at so far in this class, because we've tended to always have a root in our tree. This is more a discrete math kind of tree where we're simply saying it's a connected structure that's not acyclic. Or, I'm sorry, that's not cyclic. There are no cycles here, and yet everything's connected. And so if you wanted to make this into a tree like the ones we coded earlier, pick any vertex to make that the root, and everything else will sort of go from there. So if C was the root, you'd have A as a child and G as a child, and G would have E as a child, and E would have D, B, and H as children, and H would have F as a child. So you can pick any node to be the root and arrange that as a tree with a root. The point here is that just in general, that's a tree structure. As far as discrete mathematics, we'll discuss it. You don't have to have a root. You just need to say, well, I've got some nodes and they're connected, but there's no cycle. So anyway, there's the example of a spanning tree. It's a tree that covers the graph, spans the graph, includes all the vertices. And we will always, therefore, by definition, have v-1 edges in a spanning tree because we have v vertices, and we always have one fewer edges. Now we can talk about the cost of this tree, and just as with Dijkstra's algorithm last time, where we said the cost of a path was the sum of the weights, likewise the cost of our tree will be the sum of the weights. So we have here 15 plus 3 is 18, plus 7 is 25, plus 9 is 34, plus 5 is 39, plus 1 is 40, plus 8 is 48. And the cost of this tree is 48. And when we talk about the minimum spanning tree, what we're talking about is which tree, or there may be more than one, and there will be in this example, find a spanning tree that has the lowest possible cost out of all possible spanning trees in this graph. And so, of course, a brute force approach to this would be to say, well, you have your 8 vertices, now find every possible combination of 7 edges in the graph that if you put those 7 edges in, you'll have a spanning tree. And that will then produce for you all possible spanning trees. Because you always have all the vertices, and then every combination of 7 edges from here that produces a spanning tree, you say, okay, there's one spanning tree, and you put that aside. And then pick a different combination of 7 edges, and you say, okay, that's a spanning tree, and you put that aside. And then you pick a different combination of edges, and you say, oh, that doesn't produce a spanning tree. Maybe I pick 1, 2, 3, 4, 5, 6, and 7 there. And of course, I've never even included, vertex F, for example, if I just pick, these edges here. And so that wouldn't be a spanning tree, and we'd reject that. And you can keep doing that until you have every possible spanning tree that exists on this graph, and then add up all the weights of all the spanning trees, and then pick the one with the lowest weight. Or maybe there's a tie between 2 or 3 of them. And as I mentioned, this graph will have a tie between 2 possibilities. Now, that certainly is a possible approach, but it's going to take a very, very long time, an unsatisfactorily long time. And so what we would prefer is an algorithm to find the minimum spanning tree in a somewhat shorter amount of time. And so that algorithm that's going to take a shorter amount of time cannot afford to be churning through every possible minimum spanning tree. It needs to be able to create a tree as it goes, selecting things edge by edge, but knowing the edge that's selected is legal for the tree. And it turns out that this problem can be solved in a manner by which we'll basically, at every step, and the 2 algorithms will differ in what a step constitutes, or I should say what constitutes a step. At every step, we will pick the best possible edge from the choices available to us. And again, the 2 algorithms will differ based on which edges are available to us at each step. But we will pick the best possible edge at each step, and that then is guaranteed to be a good edge to add to the tree overall, an edge of the minimum spanning tree overall. We don't have to do any sort of long-term analysis of that edge. We simply say, well, given this algorithm, it presents to us this choice of edges at this point, whatever that point happens to be. And we'll look in detail at both algorithms in a moment. And so the algorithm will perhaps offer us, the C to D edge and the A to D edge and the D to E edge or whatever. And then we say, well, out of those edges that it's offering us at this point in the algorithm, pick the lowest weight edge. And if we do that, we know for sure then that that will be an edge that will be in the minimum spanning tree. There's no sense of saying, oh, if I'm trying to pick between the edge of weight 1 and 2 and 9, and those are the edges the algorithm presents me with, well, I could pick 1, but that's going to cause problems later on, and I would have been better off picking 2. That's not the case. This is a problem known as the 2 algorithms we'll use to solve this are both known as greedy algorithms, and that's not a term you need to know for this class. It's more of a theory term, but just so you know what kind of algorithm this is, it's known as a greedy algorithm, and that the idea is at any step you can pick the best local option, and it'll be a good global choice. So if I'm faced with picking between the edge of weight 1, the edge of weight 2, and the edge of weight 9, we'll go ahead and pick the edge of weight 1. And even though we haven't considered any other edge or how that might affect the rest of the spanning tree, we had simply said at this point, I have 3 edges, pick the best one, and I know that long term that'll be a good choice. It was a good choice out of just those 3. When you kind of take the view of the entire algorithm, that'll also be a good choice. And algorithms that proceed in that fashion, where you just kind of locally, at each step, you pick the best choice for that step, and it turns out to be a best pick overall. That's known as a greedy algorithm. And like I said, we're not going to test you on that term, but it does show up in past exams. We don't test on it anymore. But anyway, these are both going to be known as greedy algorithms because they work by allowing you to make the best local choice. You don't have to sort of look 10 steps in advance like you would if you played chess or something like that, where the best choice in the immediate moment, the best short-term choice, might not be the best long-term choice. Or even just living your life. You could choose to go out and have fun instead of study, but then you might not do well on an upcoming exam or whatever. And so often the best local choices are not, they seem great at the short term, but they're not good long-term choices. And similar with algorithms. I'm not trying to kind of wax philosophical or anything like that, but it's one possible description of a non-greedy situation. And so the 2 algorithms we look at will be greedy algorithms. And the first one we're going to look at to solve this problem is known as Prim's algorithm, presumably named for someone named Prim, but I couldn't verify that myself because I've never cared enough to check on that. I think it's Edward Prim, but I could be wrong. Anyway, it doesn't matter to you, so I will stop babbling. And the idea behind Prim's is you start out with with 2 sets of vertices, included, which we'll just call S, and included, which we'll call N. And we start out S equals some start vertex. You pick your start vertex. N equals all other vertices, and your minimum spanning tree, which we will abbreviate MST, has only the start vertex and no edges. So for our example graph, we can say that S is going to be equal to the vertex A, and N is going to be equal to the vertices B, C, D, E, F, G, and H. And of course, the minimum spanning tree has no edges. And so we're going to draw the minimum spanning tree on one piece of paper, and we will draw the graph on the other piece of paper. Actually, I think maybe I'll do it a little bit differently. I prepared some slides, and it just occurred to me that might be a better way to do this. So I'll be drawing the tree underneath the graph. So we'll start out like this. And here is our tree at this step. We have just A and nothing else. Now, the way the algorithm is going to proceed then, that's the initialization. So we've started out with two sets of vertices. The vertices that are not included or are in the set N are not part of the tree, and the vertices that are part of the set S are in the tree. And that's always going to be the case. It's the case initially. We said the start vertex was A, and so that's in the tree, and all the other vertices were in set N, and those were not in the tree, because the spanning tree right now has only the start vertex and no edges. And now what we're going to do is going to loop V minus 1 times, because each time add one edge. And one vertex to the minimum spanning tree. And so that's why we loop V minus 1 times, because the whole goal here will be every pass through the loop, we now add one of the remaining 7 vertices and one of the 7 edges we want to this graph. And we say consider all edges endpoint in S and one endpoint in N. So the edges we look at will be ones where one of the endpoints is in the tree. Because right now, the only edges we'll be able to pick will be edges with A as an endpoint, because A is the only vertex in the set S. And so that's what we had over here before when we had drawn this up. We said we'll start out with S containing just the set A. So right now we're saying consider all edges that go from A to something else. As we move vertices to S, we'll continue basically the same process, except it won't just be A we'll have open to us. We'll always be saying consider all the edges that go from S to N. They go from a vertex in this set to a vertex in that set. And so what this will restrict from us is, firstly, we won't be able to add edges out of the blue that don't have any endpoints in the tree yet, because as vertices get added to the set S and then later on added to the tree as well, we will always then, since every edge we want to add has to have an endpoint in S, it has to be connected to the tree. So we're always going to be adding to the existing tree so far. By way of an edge we add, we'll have one endpoint in the tree already. But since both endpoints can't be in the tree, we're not allowing ourselves to add edges that go between S and S, a vertex in S and another vertex in S. What that means is that we will not have any cycles. Because the only way to have cycles is to say, well, these two vertices are connected already, and if they're both in the tree already, they're both connected to each other, and then to connect them again directly with an edge, and that would cause a cycle, as we'll see. So some of this stuff I'm just sort of introducing to you, but it may be hard to visualize. Don't worry about it. I'm going to point it out again as we arrive at those positions in the example. And so right now I'm just sort of giving you an introduction, kind of have these thoughts loose in the back of your head, and then I'll repeat them when we hit the appropriate spots in the example. So we will consider all edges with one endpoint in S and one endpoint in N. That guarantees we're always adding to the tree, but we won't be causing cycles, because the fact that one endpoint has to be in S means we're adding to the tree. The fact that one of the endpoints has to be in N means we're not adding an edge between two already connected vertices, and therefore can't cause a cycle. And out of all those edges, pick the lowest weight such edge, and we'll mention ties to break however you prefer. So if you're faced with 4 edges and 2 of them have weight 1 and 1 has weight 5 and 1 has weight 8, you definitely, of course, want one of the 2 edges that has weight 1, because those are the lowest weight edges. But either one is okay. It does not matter whatsoever which one you pick. And then you say, add that edge, and the N endpoint to the tree, move vertex from N to S. And that's basically all there is to it. Of course, it's easier said than done, because this may not make sense yet until we go through an example. But this is basically the algorithm. What we're going to be doing is we will pick an edge at each step, look at all the edges that are offered to us, and pick the lowest weight one. Once we've got an edge, we know one of the endpoints is in the N set, because that's how we selected the edge. And so that vertex that's in the N set will move to the S set instead. So by the time we go through one pass of the loop, the N set will lose a vertex and the S set will gain one. And of course, therefore, if we do this v minus 1 times, we'll one by one move every vertex from the set N to the set S. And so at the end, all the vertices will be in set S. And then notice here we're also saying add the N endpoint to the tree. That means whatever vertex we're trying to move from the set N to the set S, at the same time it's going to be added to our minimum spanning tree. So as we move the vertices from N to S one by one, we're also going to be moving them, adding them into the minimum spanning tree one by one. At the end of our v minus 1 passage through the loop, when all the vertices have been moved from N to S, they've also all been added to the tree. And so at that point, all our vertices will be in the tree, and also, since we've added an edge each time, we'll have the 7 edges connecting them. So there's our starting graph. And we had said, consider all the edges with one endpoint in S and one endpoint in N. And that's those edges. And let me go ahead and write the tree down here again. Those 3 edges I've marked with the green line, at the edge of weight 3, the edge of weight 2, and the edge of weight 13, those are the vertices that go from set S to N. I can even go ahead here and write in these sets. The set S here is A, and the set N here is B, C, D, E, F, G, H. And so those are all the edges that go from set N, or from set S to set N. There's only 3 of them. And so we pick the lowest weight edge, which is the A to D edge of weight 2, and we add that edge and the N endpoint to the tree. That is, we add the A to D edge and the D endpoint to the tree and move D from S to N, giving us this graph. And so at this point now, the tree, we've added the A to D edge and the D endpoint itself, of course, to the tree. Our S now holds A and D, and the N set is B, C, E, and F, G, and H. And I've darkened in blue the edge we've added, but I'll also draw the tree down here, partly because I'm not sure how thick you can see that. And so that's the end of the first step. We looked at all the available edges, we picked the lowest, and we added it to the tree. And so now we're at the top of step 2. And again, we want to consider all the edges that go between set S and set N. But now we have 2 vertices in set S and 6 vertices in set N. And so what I need is all the edges that go between A in any of those and D in any of those. And I've got the marked in green in this picture. 2 of them we were able to consider before. The other 2 edges that go from A to something. But now that we've added D to the tree, we also have the option of adding the edges that go from D to something else. Effectively here, what we're saying is we're considering those 2 edges, and I'm just drawing them with brief, small dotted lines, and those 3 edges. All the edges that proceed from A or D to some other unknown vertex, some other unadded vertex. Those 5 are what we're picking from. And out of all of those, the lowest is the D to C edge that is of weight 1. And so if we add the D to C edge and the vertex C to our tree, then you can see them darkened in here. More generally, we've got here the A and the D edge. This was of weight 2. And now we've got the D to C edge of weight 1 that we've also got. And along with adding C and the DC edge to the tree, we move C to the S set. So we have here A, D, and C in the S set. And we have B, E, F, G, and H in the N set. And now we can say, well, consider the next step. Now we're at the top of step 3 because we've now added 2 edges. Top of step 3, again, consider all the edges that go from set S to set N. And here we have anything that goes from A to B, E, F, G, or H, and there's 1 such edge, and I've marked, that's the one we've had marked in green for a while. I have the edges D to E, which we had considered before, and D to G, which we considered on the last step. We had 1 more edge from D in the last step, but that's what we've just added. And now there's also a new edge from C that is being considered. And so those are the 4 that are marked in green in the picture there, the edges of weight 15, 11, 9, and 13. The edge between A and C, notice I've got a black X on that edge. The reason being now A and C are in the same set. And this is why we don't allow ourselves to consider edges that go between 2 vertices in the same set. A and C are already connected one way through D. If I was to connect them directly now, that would mean that there's now a cycle because I already have A and C connected one way because they're both in the tree, and then following the edge I might add directly to A, I'm back at my starting point. I've got a cycle, and trees don't have cycles. So I cannot add this edge. Now that C has been moved to set S, just like A was in set S, now the A to C edge is no longer possible to add. And so we put an X there, and that's not considered. And likewise, we only have 4 proposed edges here. The A to C edge is now no longer a possibility to add to our tree. And so out of those 4 edges, which is the lowest? Well, we have 15, 11, 9, and 13. 9 is the lowest, and that's the D to E edge. So we're going to add the D to E edge and also add E to the tree and also move E from N to S because those are the rules. The lowest weight edge that we pick, you add that vertex and that edge to the tree, and that vertex also moves from set N to set S because it's now part of the tree. And those are the vertices that S holds, the vertices that are part of the tree. So now you can see here in this picture the D to E edge is made a little darker, and I've also got here A, D, E, and C. So this is my tree up to this point, where this is 2, 1, and 9. The set S consists now of A, D, C, and E, and the set N consists of B, F, G, and H, and that's the next step in the algorithm. So now we've been through 3 of our 7 loop passes. We've added 3 new vertices. And now we start the 4th loop pass, and we say, well, out of all what are the edges that go from set S to set N? and we have all the edges that go from A to either B, F, G, or H, and we have one edge, which is marked in green up there. We have all the edges that go from D to B, F, G, or H, and we have only that edge, the D to G edge, which is marked in green up there. We have all the edges that go from C to B, F, G, or H, and we have only the C to G edge to consider there. And all the edges that go from E to B, F, G, or H, and we have 4 of those. E is connected to all of those 4 vertices, so we have 4 such edges to consider, and those are the ones marked in green right there. So I've sort of drawn dotted lines here, but they're also marked with green lines through them up there. So now this is the most edges we've ever considered. There's now 7 different possible edges to look at, one of which we've been considering all along, the A to B edge, and we keep deciding there's better edges to add at the moment, and 4 of them which are just brand new being considered for this pass. And what's the lowest of all of them? Well, the lowest of all of them is the E to B edge, which is of only weight 1. And so we're going to add that edge to the tree, and thereby adding the vertex B to the tree, and therefore B should move from set N into set S. And so that means now in the next diagram, the E to B edge will be darkened in, and indeed it is. And our set S now has all the other vertices, A, D, C, and E. It also has B. And our set N has F, G, and H. And the tree looks like this. We have here A, we had D, we had C, we had E, and we had B. And we had here 2, and 1, and 9, and 1. So now we've been through 4 of the 7 loop passes. We've added 4 new vertices outside of A. We've added 4 new edges when we had none to start with. And so we have 3 more loop passes to go. But that's the minimum spanning tree so far that we've been building. So now we go through step 5 in the loop, and the same procedure continues. We say, well, which vertices, which edges go between set S to set N. And now notice, because B has been added to the tree, now the A to B edge that we've been considering for so long is no longer a possibility. It was always, you could always hold out hope that maybe that edge would be added. Not that it's a very expensive edge, so you wouldn't really hold out hope. But, there's always a possibility that that might have been added. But now that A and B are both part of the tree, adding that edge now would connect them a second way. Since they're both part of the tree, they're already connected through the ADEB path. And if I was to add that edge, I would now create a cycle by connecting A and B a second time. And trees don't have cycles. And so as a result, then we don't want to add that edge. And so that has now got a black X through it, and we won't be considering that. So we have on this step the one edge we are considering from C, the one edge we were considering from D. We just picked one of those 3 edges that came from E, but we have 3 more that we might consider. And there's also this edge from B to F that could have been a possibility as well. And so we have here 6 possibilities, 2 here, 3 here, and 1 from B. And the lowest of 15, 11, 7, 5, 6, and 6 is 5, the E to H edge. And so the E to H edge will be the one we add on this 5th pass through the loop. We'll add the endpoint H along with that. And of course, along with that, H is going to move from set N to set S. And so that leaves us with this picture, where this is our tree. We had here A and D and C. This was 2, that was 1, this was 9, this was 1 to B, and this was 5 to H. This is the edge we've just added, the E to H edge of weight 5. Our set S is now consisting of A, D, C, E, B, and H. And the set N consists of F and G. We've gone through 5 passes of the loop, added 5 vertices, added 5 edges. So now we start pass 6, and we ask ourselves again, what are the edges that go from set S to set N? And the answer is, well, anything that goes from A to F or G, there are no such edges. Anything that goes from C to F or G, and there's one such edge that we've considered a few times now. Anything that goes from D to either F or G. Anything that goes from E to either F or G, and there's 2 such edges. anything that goes from B to either F or G, and anything that goes from H to either F or G. Those are the 6 edges we can consider, and I've got them marked in green. Oh, I'm sorry, there's also a 7th one here from H to F. So those are the 7 edges we're considering, and I've got them marked with, you know, one green slash on the graph. And we've got, of course, the same 2 edges we can no longer consider, and there's now at this point every edge is either, you know, we're down to a few enough vertices left that now every edge, there's no edges that haven't been dealt with in some way. They're all at this point either part of the tree, or we have a black X through them, or a green line through them, but that isn't anything of consequence. So those are the 7 possibilities, and the lowest of those out of 15, 11, 7, 4, 6, 6, and 8 is 4, the G to H edge. So the G to H edge will be what we add next. And with that, we're adding G to the tree, and we're moving G from set N to set S. And so by doing that, by adding G to the tree through this edge, we're now going to negate those 3 edges as possibilities, as we'll see in a moment. Or I guess as you can see here, but I'm not going to talk about it quite yet. So then that being the edge we've added, this is now our spanning tree. We have A, D, and C, and I have here E of weight 9, to B of weight 1, to H of weight 5, and to G of weight 4. And the S set here is equal to A, D, C, E, B, H, G, and the N set is equal only to F. So on the 6th pass through the loop, we remove vertex G from set N, add it to set S, and add the H to G edge. So now, on the 7th and final pass through the loop, we're asking what edges go from set S to set N. And at this point, it's easy, just like it was at the very start, because just as at the very start there was only one edge in S, at this point there's only one edge in N. So we're basically saying, what are the edges that go from anything else to F? And it's these 3 here. The one from B to F, from E to F, and from H to F. All the other vertices that haven't been added, or sorry, all the other edges that have not been added yet to the tree are impossible to consider. We had already explained the A to C edge would cause a cycle, and the A to B edge would cause a cycle. And likewise now, the C to G, D to G, and E to G edges that we had been considering before, we've now got them marked with a black X in the picture, because they would all cause a cycle. Now the G is also part of the tree. We know that C and D and E and G are all connected to each other through the C, D, E, H, G path there. And so adding another edge directly between C and G, or between D and G, or between E and G would cause a cycle, and we don't want to do that. So we only have 3 possible edges left to add, and we have to pick one of them, and that will complete the minimum spanning tree. And here we have 8, 6, and 6, and so we have a tie between 2 edges of weight 6, and we can go ahead and pick either one of them. We'll pick the E to F edge just because, you know, why not? We could have just as well picked the B to F edge, but we didn't. And so that leaves us with this, and the final minimum spanning tree is now A, D, C. Here's 2, 1, 9, B, H, here's weight 5, G we have here is weight 4, and F here of weight 6. And if you'll notice now, we don't have any more edges to consider because we're done with everything. But if you were to write these out, set S has all the vertices, A, D, C, E, B, and H, and G, and F, and set N is empty. And so there are no edges that go from set S to set N, and likewise you can see here we have the 5 X'd out edges from before, and also now F and H and F and B are impossible to add because F is now a part of set S as well. And so this is our minimum spanning tree, and the weight here, the total cost is 3 plus 9 is 12, plus 1 is 13, plus 9 is 22, plus 6 is 28. And so our cost here is 28, which is less than the 48 we had for the example I put up earlier. I believe the example I put up earlier was weight 48. Checking the old slides. Yes, the previous cost of this tree had been 48, and the one we've now created is cost 28, and that's much better. Now, proving this algorithm works is beyond what we're going to do in this class. You'll do that in a later class, a theory class, either 273 or 373. Though I guess you probably wouldn't be taking 273 through the remote stuff. But if you take 373, I think they do prove that in that class. So that's where you'd see the proof that this works. We're not going to prove that it works. We're simply going to talk about the implementation and the running time in the next lecture. We're not done yet. But we're not going to worry about proving the mathematical correctness of the algorithm. Just take my word for it that it works, and the proof is left for a later course. But that's how this algorithm works. That's Prim's algorithm, and it produces the minimum spanning tree. Now note that if we had picked the B to F edge instead of the E to F edge, we would have ended up likewise with another minimum spanning tree. It just would have had a different edge. So we really have two different minimum spanning trees in this graph. They're, of course, both across 28, but the difference between them is one of them has the edge from E to F, and the other wouldn't have that edge, but would have had the edge from B to F. That's one possibility when we end up with a tie. We have here two edges that we are picking between. Sometimes you'll pick between two edges, and then that results in two different trees, like we have here. Sometimes there might be two edges of the same cost, and they will end up both in the tree, so if you pick one, the other one gets picked later on. Now, we never faced that situation here, but in the next algorithm we'll see, we'll at some point have a tie between the C to D edge and the E to B edge, which are both of weight 1. We'll be, as we'll see with the next algorithm, forced to pick between those two edges. And when we pick between those two edges, we're going to proceed to add whichever one we didn't pick as the edge in the next step. And so sometimes when you're forced to pick between two edges, the other one eventually gets added anyway, and so the order didn't make any difference, and you have the same tree, just you added the edges in different orders. Sometimes when you're forced to pick one edge or the other, it then prevents the other one from being added, and so you see both examples here. In this case, there's two edges of weight 1. They've both been added to the tree. In this case, there were two edges of weight 6. We can only add one of them to the tree. And our algorithm actively had us picking between these two. It didn't actively have us picking between these two, but it will in the next algorithm we look at. So that's Prim's. It's going to turn out, and then the implementation for this, which may look kind of complicated, because how do we keep track of which vertices are marked with black X's, or which edges are marked with black X's, and which ones are marked with green lines? It's going to turn out that that's actually there's a very straightforward way to do that, based on Dijkstra's algorithm. And we'll talk about that just after talking about Dijkstra's algorithm implementation in the next lecture. The other algorithm is known as Kruskal's algorithm. And likewise, it's a greedy algorithm, but it works a little differently. The initialization step here will be to include all vertices, which means initially things will be unconnected. With Prims, we were always building a tree at each step. We had one vertex, we added another edge and another vertex, another edge and another vertex. And we always, as we went through step by step, always had a mathematical tree construct. Here, our initial setup is going to be all the vertices. So we don't really have a tree to begin with. Let me go ahead and draw the graph up here again. We have here A, B, here's 13, 3, D is 1, A is 2, to E is 9, to B is 1, to F is 6. We have 6, 8, to H, and then this was 5, to G was 7, to 2 here was 4, and this was 11, and this was 15. So that was our graph, and initially our minimum spanning tree is just going to look like this. We'll have A, C, G, D, H, E, B, and F. We simply have the 8 vertices, no edges at all, and so this certainly is not a tree by any stretch of the imagination. It's 8 vertices floating in space. So initially things will be unconnected. We have no edges. And all edges are considered unmarked or unconsidered, because we haven't really done anything yet. So at this point, all the edges are unconsidered. And then the algorithm was basically going to say loop, again, v minus 1 times. Every time through the loop, we add an edge each time. And what we will say here is we'll loop v minus 1 times, pick lowest edge that doesn't cause a cycle and add it. I'm going to expand this loop on the next page, but this is now fitting it all on one page. That's the essential idea behind Kruskall's algorithm. We're going to pick the lowest edge that doesn't cause a cycle, and we'll add it to the tree. So let me expand on that just a bit. And that's sort of the quick summary. The way this loop is really going to run here is we can say loop v minus 1 times. And we'll say out of all unconsidered edges, pick lowest one, mark it considered, whatever that means, however we make that marking. Because now we're considering it. We've picked the lowest edge, and we're saying, well, now this is an edge we've looked at. If it won't cause a cycle, if we add it, and we're done with this loop pass. So if the edge we're considering can be safely added, then we'll go ahead and add it, and we're done with one pass of the loop. Otherwise, reject edge, pick again. That is, go back up there and pick again. And we won't finish this pass of the loop until we've actually gotten through it with an edge to be added to the tree. So we can run this collection of stuff inside the loop many times. It's sort of a loop within a loop in the sense that every time we actually pick an edge, that finishes the loop traversal. But within here, there's sort of a smaller loop that we keep picking edges over and over and over until we grab one we don't reject. And so that's this loop within a loop here. We could pick the first edge we look at in this pass. We could reject 5 edges and then consider, and then pick the last edge. But basically, we just say for every pass in the loop, we keep looking at the edges from lowest to highest until we find one that can be added to the tree, and then we'll add it to the tree. So, by way of an example, here's the example. And we can go ahead and consider, maybe we can rank the edges. We have the B to E edge, which is of weight 1. We have the C to D edge, which is of weight 1. We have the A to D edge, which is of weight 2. We have the A to C edge, which is of weight 3. We have the G to H edge, which is of weight 4. We have the E to H edge, which is of weight 5. We have the the E to F edge, which is of weight 6. We have the B to F edge, which is of weight 6. The G to E edge, which is of weight 7. This 9 here, let me go ahead and write up here. The H to F edge, which is of weight 8. The D to E, which is weight 9, and hopefully now it's a little clearer that that's the case. And I think we've only got 3 more. The D to G edge, which is of weight 11. The A to B edge, which is of weight 13. And the C to G edge, which is of weight 15. I've got here 3 edges, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 4, 5, 6, 7, 8, 9, 10, 11. I got them all. So those are our 14 edges ranked from low to high. And the way we're going to do this is we'll say, well, now pass 1. pick the lowest vertex that hasn't been considered, or pick the lowest edge that hasn't been considered at all yet, which is this one here. And can that be added to the tree without causing a cycle? Yes, it can. That's the B to E edge of weight 1. So this is added on step 1, and we're done. Step 2, the next edge, C to D of weight 1. Can that be added without causing a cycle? Yes, it can. So that's the edge chosen on step 2. Next step, the A to D edge of weight 2. That's the next lowest edge. Can that be added without causing a cycle? Yes, it can. So we'll add that edge. That's chosen on pass 3. And indeed, in general, the first few passes through the loop will accept right away. We haven't added enough edges yet to be causing cycles. But now we can, because now the fourth of the 7 passes through the loop, we hit the A to C edge of weight 3, and as we can see, if you add that, that would cause a cycle between A, C, and D. And so that one is rejected, and we have to pick again. We're not done with the fourth pass yet. We've now had 1 rejection, and we do this loop back now, where I say, the first 3 passes were easy. Pass 1, the first edge I'm considering is successful. Pass 2, the first edge I'm considering is successful. Pass 3, the first edge I'm considering is successful. Pass 4, the first edge I'm considering is rejected. I have to loop back up and pick again. So I'm not done with pass 4 yet. I haven't picked my 4th edge. I now look at G to H. And that indeed can be added without causing a cycle. So that will be edge number 4. On pass 5 of 7, E to H can be accepted right away. That won't cause a cycle. On pass 6 of 7, this was supposed to be EF. That can be added right away without causing a cycle. So that's edge number 6. On pass 7 of 7, E to F now would cause a cycle between B, E, and F, so that's rejected. So we continue past 7 out of the 7 we'll need to do. G to E will cause a cycle between G, H, and E, so that likewise needs to be rejected. And so now we've had on past 7 2 rejections. We consider HF. HF would cause a cycle between HF and E, so we reject that. And so now in past 7 we've had 3 rejections. And finally we consider DE and weight 9, and there we go, that one's okay, and that's our 7th edge we add. Now you can finish going through. You of course reject all of those as causing cycles, but at this point we've added 7 edges, we know we're done. And so that's the minimum spanning tree result there. And that's of course the same tree we had last time. If I had listed BF before EF, then I would have picked BF instead, and I would have rejected EF, and we would have gotten the alternative answer that we spoke of before. So here we had a tie between 2 of these. We ordered them that way. Here we had a tie, but they both eventually got added. Here we had a tie, and depending on which one came first, that one would be added and the other one wouldn't, just like I spoke of before. And so there's your minimum spanning tree. And so the idea here is we had 7 passes to the loop to add 7 edges. The first pass was fine. Second pass, first edge was picked. The third pass, the first edge was picked. On the fourth pass, we rejected 1 edge before picking 1. The 5th pass of the loop, the first edge we looked at was picked. The 6th pass of the loop, the first edge we looked at was picked. And on the 7th pass of the loop, we rejected 3 edges before picking the 7th edge. And that's Kruskal's. There's nothing more to say about that. Kruskal's is usually an easier one to do by eye because you can sort of list the vertices or list the edges in order, sort of look around and say, okay, I see 2 edges of weight 1, and there's an edge of weight 2. With prims, it's often harder to keep track of which edges can be considered on the next step by eye. Computers, of course, can, as long as you code things right, can do either one just fine. But usually, if we're going to find just by eye, looking at a minimum spanning tree, usually for a pretty decent, a small enough graph, Kruskal's would work just fine by eye. It's usually the way we would approach this. But anyway, those are the 2 minimum spanning tree algorithms. There's not really much more to say about either of them. And that's that. What we will look at next time is first the implementation of Dijkstra's and then the implementation of both of these algorithms. And it might bleed a bit over into the next lecture for the local folks. I'll make sure I'll cover everything, so the next lecture might be a little bit longer, but I'm going to try and get it done within the 50 minutes or 55 minutes or whatever that I normally would take to do so. So that's it, and I will see you next time. In the meantime, consider how you might implement both Dijkstra's and Prim's and Kruskal's. Prim's and Dijkstra's will be very close in implementation. Kruskal's will be definitely different. But before you review the next lecture, give some thought to how you might use the data structures we've studied so far to implement those 3 algorithms, and then we will go over that issue at the next taping. See you then.